let's do some examples from section 7.3, and these are linear programming problems. So the first thing we're going to do is define our variables. So let's see, we have x equals, we're replacing shocks. So the number of shock replacements. And then y equals, let's see what else is going on. We're replacing brakes. So the number of brake replacements. And then we're going to make a chart because I'm just finding that's really helpful for organizing this information. And then we have information about the amount of time. So 3 hours for shocks and 2 hours for brakes. Then we're also given information about cost. So the labor cost for shock replacements is $500, and the labor cost for brake replacements is $300. So first we have a limitation on the number of hours per week. So we have 3 hours for each shock replacement times X shock replacement. So that's the total time for shock replacements, plus 2 hours for each brake replacement times the number of brake replacements, Y. And that has to be less than or equal to 48. That's our limitation on the amount of time we are able to spend. So then we need to write an objective function about the thing we're trying to maximize or minimize. Well, we're trying to maximize income. So Z is going to be income. So for each shock replacement, I get $500 times the number of shock replacements, so that's the X, plus 300 for each brake replacement times Y, the number of brake replacements. So look for patterns in these problems. There's a lot of patterns that keep coming up over and over. Okay, so then the next thing we need to do is graph the feasible region. So we need a coordinate system. Don't forget to label it X and Y. And then we need a couple more inequalities because we have a little bit more information given here. At least 2 shock replacements. So X has to be at least 2. And at least 6 brake replacements. So Y needs to be at least 6. Okay, so very, very often the inequality that you need to graph is going to be easiest to graph if you use the intercept method. It's just very common in these problems. So when X is 0, Y is 24. And when Y is 0, X is 16. So both of those are divisible by 4. So I think I'm going to use, actually I think I'm going to use increments of 2 for each box. 2, 4, 6, 8, 10. 2, 4, 6, 8, 20, 24, so that's far enough. And then on the Y, 2, 4, 6, 8, 10, and 2, 4, 6, 8, 20, 24. So when X is 0, Y is 24. And when Y is 0, X is 16. So the line goes between these 2 points. There's my line. And now I need to decide which side to shade. So let me test 0, 0. And if we put 0 in for X and 0 in for Y, we get a true statement. So I need to shade towards 0, 0. Okay, so then I have the restriction that X needs to be at least 2. So the line X equals 2 is a vertical line. Here's the line X equals 2. And X is greater than 2 I find to the right. And then I need Y is greater than 6. So I need to graph the line y equals 6, and I need y values above. So x values to the right of x equals 2 and y values above 6. So our feasible region is this triangle that's triple shaded. So it's got all three of these inequalities are true only inside this triangle. Everywhere else, only one or two or none of the inequalities are true. So this is our feasible region. It's the only places we can operate. Well, the corner point theorem tells us that z will be maximized and minimized only at corner points. So those are the only points you have to check. So we need to find the corner points, and we can see the bottom left corner one. That's going to be when x is 2 and y is 6. So that one's easy. Well, the next one we have to use algebra to figure out, because for the next one I have x is 2. So let me label these corner points A, B, and C so you know which one I'm talking about. So A is 2, 6, but then B needs some algebra to figure it out. So x is 2, and then 3x plus 2y is 48. So I need to put 2 in for the x and solve for the y. To find the point of intersection of two lines, you solve the system of equations. So I have 2y equals 42 and y equals 21. So 2, 21 is my second corner point. And then the third corner point happens when y is 6, intersects with 3x plus 2y equals 48. So I can put 6 in for the y and solve for the x. And get x equals 12. So 12, 6. That's our third corner point. And make sure that makes sense on your graph. Like, look at it and say, yeah, that seems reasonable. Okay, so here's our three corner points. 2, 6, 2, 21, and 12, 6. So then we need to evaluate z, which equals, come up here and see, 500x plus 300y. So 500x plus 300y. Okay, so let's evaluate z at each of these points. So at the first point, z equals 500 times 2 plus 300 times 6. So that looks like 2,800. And then at the second corner point, z is 500 times 2 plus 300 times 21. Clearly, that's going to be more. Let's see, 300 times 21 is 6,300 plus that 1,000 is 7,300. And then at the third corner point, I have z is 500 times 12 plus 300 times 6. And I'm getting 7,800. So remember, we're trying to maximize income, so we want the biggest number. If this was a cost function, we would be looking for the smallest function, the smallest result. So the maximum income is the $7,800. It will be achieved when 12, let's see, and our X was, I like to write it out, shock replacements. When 12 shock replacements and 6 brake replacements are done. So that's our final answer, and that's all the steps of a linear programming problem. So collect information, organize it, write your inequality that describes your limitation, all your inequalities. Write your objective function, graph your feasible region, find your corner points, evaluate z at each corner point. Okay, so let's look at one more example. And this is an investment problem where we're going to invest at most $50 million in treasury bonds with 4% annual interest and mutual funds paying 6% annual interest. So we have two things. So I'm going to let X equal the dollars invested in U.S. Treasury bonds, and Y equals the dollar invested in mutual funds. And then I'm going to collect my other information that I've given here. So the interest rate on the treasury bonds is 4%, and on the mutual funds is 6%. So the $50 million is the total, so you want X plus Y to be less than or equal to 50 for the total. Then we can write an inequality about interest. So to find the dollars of interest, we multiply the percent of interest times the total dollars for each investment vehicle. So 4% of the money in the treasury bonds plus 6% of the money in the mutual funds. And that's going to be our interest. And this is going to be our objective function because we want maximum annual interest. Okay, so let's keep reading. The plan is to invest at least 20 million in bonds. So X needs to be at least 20 million. And at least 6 million in mutual funds. So at least 6 is what we have for Y. And then bonds have an initial fee, so let's collect this information. Bonds have an initial fee of $300 per million. And mutual funds has a fee of $100 per million. So I also have a limitation on fees because the manager is allowed to spend no more than $8,400 on fees. So let's write that as an inequality of $300 per million times X, because we're going to write that X is in millions of dollars, and then we don't have to write so many zeros. And Y is in millions of dollars. So 300X plus 100Y is going to be the total of the fees, and we want that to be less than $8,400, but it's okay if it's up to $8,400. That would be the most we would be allowed. So how much should be invested to maximize the annual interest? So that's how we knew the interest equation was the objective function. Okay, so then you're going to need to graph these inequalities to come up with the feasible region. So I'm going to write them down real quick so that we can go to a tool that I want to show you that, especially for big number problems like this, is a really helpful tool. And it's called Desmos. So this is Desmos, D-E-S-M-O-S, and it's free. You can either use it on the web or you can get a free app for your phone. That's the same program. So let's see what happens if we put 300x plus 100y is less than or equal to 8400, and Desmos draws the inequality for us. And we can zoom a little so that we can see the feasible region better. Okay. So that was the inequality that talked about the fees. Then we had the one that said the total investment, so x plus y had to be less than or equal to 50. Okay, so then with Desmos, if you touch or mouse click on the point of intersection, it will give you that result. You'll need to show me the algebra for finding it, but you can use Desmos to double check. And then we had two more inequalities because we wanted x to be at least 20. And y to be at least 6. So there are all the inequalities graphed, and we can see the feasible region, and we can see the points of intersection. So you can use Desmos to help you see how you need to make your graph. You can see the y-intercept and the x-intercept, so you would know how big you need to make your graph. Sorry, I'm trying to get up to the x-intercept so I can see what it is. So the x-intercept, you could find those, and the y-intercepts, and so you could use that to make your own graph. Okay, so once we make the graph, then we can see where the corner points are, and we would evaluate this z function at all of the corner points, and we would want to maximize the annual interest. So if you have more questions, let me know, and if more homework example problems would be helpful, let me know that. There are examples in the textbook also that you can follow through step by step so that you can get the idea better.